Let's start equilibrium, because up till this point, all of our reactions have just been going forward. Okay? We've just been having reactants that just make product. And maybe if there's a limiting reactant, the reaction will go until that's used up, and that's done. Okay? In real life, very few reactions actually fully behave that way. A lot of reactions will say stop even before the limiting reactant is used up. And there are some cases where different conditions can cause you to reform the reactant all over again. Okay? And you can adjust the conditions like concentration and temperature and things like that to figure out to adjust how much reactant or product you have in a mixture. So this is an example of one of those such reversible reactions. And this one can be tracked because N2O4 is colorless, where NO2 is brown. NO2 is one of the main components of smog. It comes from automobile emissions that react with the light in urban areas to form this brown kind of haze to it. So NO2 gas is brown in color. Okay? So you could use a colorimeter or something to monitor the progress of this, because one of them is colorless and one of them absorbs light. Okay? Anytime that happens, you can use a colorimeter, or you can just look at it. Okay? So let's imagine, if we could, we had just N2O4 molecules, and look what happens. The N2O4 molecules break in half to make NO2. Right? So it's just like, so it's, they look like that, and then they join together and they split apart. Okay? Mm-hmm. Oh yeah. The absorption of light has to do with the form of energy that, so it has to do with the first unoccupied energy level that electrons could jump to. Okay? So when something absorbs light, it absorbs that photon, which causes its highest energy electron to hop up in energy. Okay? And depending on what that gap is, that determines what wavelengths of light get absorbed. So the entire field of spectroscopy uses that. So our colorimeters, and Beer's law comes exactly from that. So yeah, N2O4 does not absorb visible light, probably absorbs UV light or something like that. But NO2 is brown in color, which means it probably absorbs blue light or something like that. So imagine starting with pure N2O4. We had a container, it only had N2O4. Okay? The forward rate, okay, forward is there, reverse, okay, just by definition, forward is reactants to products, but reverse is going the other way. Okay? So if we start with pure N2O4, the reaction of N2O4 becoming that product starts fast. Because that's the time when we'll have maximum N2O4. Okay? We'll have the most N2O4 possible, so the forward reaction will never be faster than when it's just N2O4 in that container. Okay? The reverse rate starts at 0, because there's no NO2 initially, like we set up. Okay? Everybody with me so far? If all we have is that reactant, the only thing that it can do is make product. Okay? And if there's no product to start with, we start with no reverse reaction at all. Okay? But as more product is formed, what will happen to each of those rates? What will happen to the forward rate as we begin consuming that reactant? It'll decrease. Decreases as N2O4 is consumed. And that reverse reaction that started out as nothing because we had no product there, what will happen to that over time? That will increase. As soon as we start producing some of that product, we now have the opportunity for that reverse reaction to also happen. Okay? So that increases as NO2 is formed. Okay? So we have a forward rate that starts high but is lowering. We have a reverse rate that starts at 0 but is raising. At some point, what's going to happen?
It'll be the same.
You got it. Eventually, both rates will be equal. And that's the definition of our chapter. Okay? We've called it dynamic equilibrium. And we only have to say that once anymore because just comparing it against static equilibrium, which you'll learn about in physics or engineering or something. That's just weights on either side of a teeter-totter or something like that. Okay? But dynamic equilibrium is things where both things are continuously happening, but they're opposite and they're happening at the same rate as each other. Okay? So let's write that. Occurs when forward and reverse rates are equal. Okay. And concentration-wise, we start out with a lot of concentration of that reactant, 0 concentration of that product. Okay? The reactant, its concentration will always be decreasing, okay, because you're always using it up. Your product, its concentration will always be increasing, but then at some point, for every product that you make, one product gets turned back into a reactant. Okay? At some point, it becomes sort of like a revolving door, where every one that you make gets just, for every one that you make, one gets brought right back again. Okay? So the concentrations become, concentrations stop changing. That's a better way of saying it. Okay. But the thing is, the concentrations do not need to be the same. In fact, the concentrations will probably never actually be the same as each other. The rates will be the same. So let's do a graph of concentrations, okay, of the reactant N2O4, which starts out at high concentration, and NO2, which starts out at 0 concentration. Okay. At some point, when we reach equilibrium, it's a different color, let's use purple here. The concentrations won't be changing anymore, but as you'll see in my little graph here, they're not necessarily going to be the same. So I'm going to start out going downwards like that, but I'm going to flatten out that. Okay. And then for NO2, I start out at 0. I'm going to go upward, but then again, I'm going to flatten out right there. Okay. Their concentrations will probably not be the same. And we'll talk about what determines that. Okay? But at some point in time, their concentrations will no longer be changing. Okay? But that means that once we reach a certain point, for every forward reaction that happens, a reverse reaction will happen sort of around the same time. Okay? And it's like, I like the revolving door idea, where for every one that goes in, one comes out, and it just keeps going like that. But concentrations are pretty much not the same at equilibrium. Rates, however, will be. So let's use red here. Undo. Reverse rate, something like that. Forward rate. like that. Those are supposed to be a little more symmetrical, but you get the idea. So, as soon as forward rate and reverse rate equal each other, the equilibrium has established. I guess it doesn't need to be exactly in the middle, okay, as long as they're equal to each other. Okay. In fact, one of the ways of thinking about why their concentrations might not be the same could be if that is offset a little bit. Okay? But still, if the rates are equal, the concentrations will no longer be changing anymore. Okay? So we'll come back to this kind of graph several times throughout this chapter as just a reminder of what's happening once we've reached equilibrium. But I think the most important thing to remember is that equilibrium means that the concentrations are no longer changing. Okay? It doesn't mean that they're the same. That's, again, a common misconception, that everything is the same, and it's no. They're reached a point where they're not changing anymore. We could reach equilibrium that is centered somewhere near the products, where we've got 90% products, 10% reactants, and then it just stays there. Or it could be the other way around. It could be somewhere near the middle. It could be 99.9% products, or it could be really anywhere along this kind of continuum here, like that. It could be like that. Okay, but the key is that the concentrations have stopped changing.